right, kiddos, section 4.1. Antiderivatives, derivatives but with an anti, and indefinite integrals. Antiderivatives and indefinite integrals. If you guys remember from the beginning of the year, the very beginning, all right, focus. We had those sheet protectory things with, like, I think it was a teal piece of paper in there, and one day we had a parabola, and we did different little tangent lines. You guys worked in groups to find the slopes of different lines that went through the parabola, trying to approximate the slope of the tangent line. We were introducing differentiation, derivatives, limits first, and then the limit definition of derivatives, and then like the shortcut derivative rules that made everything simpler. But then we faced harder functions, and we had to do things like chain rule and inverse trig, and so it wasn't easy, but it made it simpler than the limit definition. But we didn't stop there at the beginning of the year. We also had another day exploration where you had a parabola, and then there was area under the parabola. And we were approximating with, I think, rectangles. Weren't we doing bases times heights, and you guys were adding together the areas of the rectangles, and you were approximating what you saw in your calculator was an integral, the little SE thing. Now, we're not going to get to the SE thing, well, first thing, but we do need to, before we can ever get to the SE thing, before we can ever get to what is called an integral, we need to think about an antiderivative. Now, what do you guys think about the prefix anti?
Negative.
Opposite, kind of. Maybe in relation to opposite, just for sake of our application, we could think of backwards. So antiderivatives and indefinite integrals, we're going backwards. What does that mean? Usually this would be an answer, right? Usually this would be an answer. But right now it's the question. What? Usually we'd find the derivative. We would answer, okay, find the derivative for something, and the answer would be, okay, the derivative dy dx or f prime of x is 5x to the fourth. Yay, found an answer. We can use it for a slope of a tangent line, yada, yada, yada. But what's changing is, guess what? Find the function f given the derivative. They're giving us the answer, and we need to figure out the question. Now, that would have been from last semester going backwards, but this semester it's going forwards with integration. Taking a derivative and trying to ask yourself the question, where did he come from? Who is his original function? Now, if you guys are looking at it, hopefully, maybe, some of you can jump there and say, wait a minute, I would have gotten this as a derivative when I was taking the derivative of what function? You guys see it? Oh, this is rough. Don't worry, Mrs. Christensen is working to get me a better solution. X to the fifth, right? Bring down the 5, make it a 4. So then we could say, what's the antiderivative of 5x to the 4th? X to the 5th. Does that kind of make sense? Now, is this always going to be easy? No. Why was this one easy? Because it was the perfect derivative. Let's say instead of x to the 5th, let's say we started with 1/2 x to the 5th. Question, what would the derivative have been that we would be starting in now that we're doing antiderivatives? If there was a 1/2, what would the derivative have been? 5/2 x to the 4th. Wait, so the coefficient could be different, but what's still the power of any derivative if you have x to the 5th? X to the 4th. So the power is going to follow an actual pattern, and so is the coefficient, but we're going to learn some rules. They're going to be called integration rules, and they're going to help us find antiderivatives, which means given the derivative, finding the original, or differentiating backwards. You guys laughing at Mr. Park's music? I'm not sure if you can hear it. Probably if you have it turned up, because remember it's turned up pretty loud. You have to turn it down if you're ever watching it.
And then you'll yell something, and then I dying because I have it on so loud. It's just terrible.
Oh man. Differentiating backwards. So being given the derivative and then going to you guys got it? being given a derivative, being given an f prime, being given a dy dx, and then going to the original function f. Now, what's something nice about being given a derivative? What would be a type of problem that you would really love to be given a derivative for?
Relative extrema.
Yeah, relative extrema, that'd be cool. If you were given the derivative, just do the pitchfork and then check your signs, you're done. There's no crazy deriving process that you have to do or differentiating that you have to do. What else would you like being given the derivative for? Okay, yeah. Right? In your card matching, you liked having the equation. You could find the derivative and then graph it and not have to stress about it. That's true. What's something else they could ask you to do with the derivative? Tangent line. You could find the slope. Now, what would be the struggle if you were given the derivative but not given the original? You could plug in the slope easy, but what would be hard? Yeah, the point would be hard. So that's kind of what you need to be thinking about with anti-differentiation. 1, we have to get used to it. 2, we have to memorize new rules to help us with the tricky ones, because we're not going to be able to, and some of you maybe wouldn't have been able to even think through this without someone helping. We have to train our brains for how to go backwards, but don't worry, we're not going to have to skip steps. There are formulas we are going to memorize. Chain rule backwards is especially tricky. There's something called U sub, and then think U prime, U sub, that we're going to have to talk about. And if you thought the inverse trig rules were hard going forwards, hopefully by studying those forever is really hard, it's going to make it easier to go backwards. So you're going to have to notice 1 over square root of something squared minus something squared and say, oh, that's an arc sine. So we're just going to have to train our brains. But don't worry, we'll have rules again. We'll have some of that integration competition in class and whiteboards again, kind of like we did in the very, very beginning with the power rule and the chain rule and the product rule and all that stuff. So that's just to give you an idea of what's coming. All right, let's keep going. So, what is an antiderivative? This is him. What is an antiderivative? This isn't my thing. This is a generally accepted mathematical community thing. To use a capital F to denote an antiderivative. And the reason being, even though it would have been the answer to a question last semester, it's the problem this semester. So they're not going to call it usually F prime for you. They're just going to call it F, because F can stand for anything, anyone. They're just going to call it F, and you're going to have to notice by the little squiggly thing, by the integral is what we call it. You're going to have to notice, uh-oh, this function inside, I need to go backwards. I need to see him as someone's derivative. So this capital F is different than little f. It's trying to kind of still let you call things f for the function. But we can't use little f anymore, not really, for the original function, because little f is, in an integration problem, is going to be what you're given inside an integral that we need to anti-derive. Yep, it's going to be forever number, aw, stink, you should, okay, I was going to say you guys should know from all of your coding, huh? Thanks for the smirks, that doesn't really help. So I think we ended at 29, was it 28? 29. Oh, L'Hôpital's is 29. Just keep going, B1 off, okay. And so our example from right before, if you want to try to match up this notation with the example that we just did a little bit ago, I am going to have to kind of make space though. There we go. When you were given dy dx is equal to 5x to the fourth, we could have rewritten this, and here's where the notation comes in. We could have taken this dx, which we saw last semester, we could multiply to the other side. We saw last semester we could multiply that to the other side when we were talking about differentials, and we could have dy is equal to 5x to the fourth. We're splitting up that dy dx notation. dx. I'm showing you how this antiderivative applies to the problem that we just did. It's just a different way of writing it. Instead of being given all these crazy directions, and it's not that bad, but find the antiderivative of, or who is the original function for, we could just mathematically move that dx to the other side. Remember, that's differential y. And then we could say, hey, it's time for us to go backwards. And we put an integral. It's an s, but elongated. Technically, I think the story goes, and I'm pretty sure it's factual, that s stood for summation. And if you think about, which most of you probably won't connect until we reteach it and teach it in more detail, integration actually represents area under the curve. When we still have variables, it's indefinite, so it's a formula for area under the curve with different x values. When we have bounds from one place to another, it's a finite, it's a constant area. Well, you can have infinite area, but that's kind of crazy. That's more of a BC thing. But anyways, little integral technically stands for summation, because if you think about those little rectangles, we're summing all the areas together. But that's okay. At this point, it's called an integral. We're just going to call it an integral and stay there. But you could integrate both sides and say, hey, that's cool. I have dy dx, but I want to go backwards. I want to antiderive. If there's nothing in this integral, we can say there's an understood 1, just like we always do in math. There's no number in front of x, it's 1x. There's no number in the denominator of 5, it's 5 over 1. There's no number in an integral, it's 1 dy. Now here's the crazy thing. If you look at this, 1 dy, we say this little dy tells us, okay, everything's in terms of y on this side, or it should be. There's a 1. What expression would have a derivative equal to 1 in terms of y? It's a weird thought, I know, but it's y itself. Remember when you guys did implicit differentiation? We would derive the y in terms of x. That's why we had dy dx. But if everything's in terms of y, no big dealio. Who has a derivative of 1? Y. Y prime is 1. Done. Dun, 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 dun. And then over here, we already talked about who has a derivative of 5x to the fourth, x to the fifth. But what's extra up above? What does C usually stand for? Constant. Why on earth would we need to, in an original function, put an arbitrary constant C? If you took the derivative of any constant, it's 0. Couldn't the original function of 5x to the fourth be x to the fifth plus 10? Sure. What would the derivative be? 5x to the fourth. How about x to the fifth minus 1? The derivative would be 5x to the fourth. How about x to the fifth plus 5,282,376? The derivative is the same. So we have to say, uh-oh, there is an unknown when we antiderive, when we take an integral. There's always an unknown plus c plus constant that could have been there and disappeared. And we're going to keep it arbitrary. We're going to keep it general, just to see, unless they give us a clue and say, oh, by the way, there's a point that also has to be true. If they give us an x and a y of the original function, then we could plug in that x and y and solve for c and be definite only one answer is possible. But without a clue, we have to say, oh, no, it could be any constant. Does that kind of make sense? And that's answering the question that you see down below. Why do we need a plus c? Let me zoom in, especially for my peoples in the back. Why do we need a plus c whenever we find an antiderivative? Because we have no idea whether or not there was a constant involved. And you can also put down something to the effect of the derivative of any constant equals 0, so we won't see it in the dy dx. Does that make sense? So I want you guys to go ahead and look at the function that's down below. F of x equals 4x cubed. If you want, you could actually think about that if it helps with what we just did. Since this is a function and we're finding an antiderivative, we could technically say, oh, hey, guess what? This guy is a derivative of somebody. Of who? Technically of capital F. So we could say, hey, you're the derivative of, not this little f, but the derivative of somebody. we could go ahead and start it off like this. Can you guys follow the notation that I did up above in the example, which is also the notation basically from up here? And can you solve for me that antiderivative? Trying to show the notation of how we can write our work of what we're doing. Now, quick heads up, we still haven't learned a formula. So you're just trying to think backwards and be like, wait, who has a derivative of 4x cubed? That comes from somebody. Looks like a power rule was done. So what would have been there before the power rule? But we will memorize formulas that'll help us if it's not an easy one to go back or backwards from. Somebody. What's the first step? Don't do the spaghetti yet. It's technically illegal until we, Jason, multiply both sides by dx. If we multiply the left side by dx, see if you guys see the last things we did last semester were getting us ready for the beginning of this semester, yeah? Finding the differential of y, multiplying the dx on the other side. Now, Brandon. Spaghetti, but let's call it by its proper name. Integral sign. So put in the integral of the left. Put in the integral of the right. If it helps, you can put an understood 1. What's the integral of the left side? Y. What's the integral of the right side? Who figured it out? X to the 4th, but did you remember to say, uh-oh, but there might be a... So we have to allow for that. How many of you guys got x to the 4th? How many of you guys got the plus c? How many of you guys does it at least make sense now that you look at it? The derivative of x to the 4th is, bring down the 4, make it a 3, 4x cubed. Derivative of c is 0. Okay. Does that make sense, kind of? Okay. Now, if we were to keep going, let's actually save this until maybe Mrs. Christensen gets me some sort of tablet-y thing. Because that's going to be kind of a mess. Let's go instead to this one. Don't worry about your notes. I'll just move this to whatever we need to go. Let's go down here maybe. Basic rules. Stink-a-dink. Even though some of you are able to think about it and say 4x cubed. Oh, I know that one. What if, before we get to the basic rules, let me show you why the basic rules. You ready? What if I was to ask you something like, solve the integral. It's called indefinite, guys, if you're wondering. Some of you that were looking for calculus jokes last semester, you saw integrals with little numbers on top and bottom. The integrals without numbers on top and bottom are called indefinite. What if I was to do dy equals the integral of... Why is this so messy? We'll do 1 dy. That's messy. Of... x to the 3/2. Oh, flame sauce. What if I was to give you this one? Where'd he come from? What? Where'd he come from? I don't know. Where'd he come from? Yay, I got half of it. I got another half. Question. When you take a derivative of an x to a power, you subtract 1. So if 1 was subtracted, we need to add 1, which is why the x cubed became an x to the 4th and x to the 4th became an x to the 5th. So if we add 1 to this, what would we get? 5 over 2. Does that make sense? Bring down the 5. Wait. Who's not there? It's a 1 instead of a 5/2. So if this comes down and has to poof away, what must have been there waiting for him? Do you see how rules might help? We're going to go ahead and look at in more depth on Monday something we're going to start probably with You guys see the power rule? Add 1 instead of subtract 1, divide by the constant because he's coming down and needs to go away. All right, cool kids, we'll work with more antiderivatives on Monday. Otherwise, pep rally schedule. See you later. My one group, don't forget to finish up today.